Okay, welcome students. So in this video, we're going to start chapter 2. We're going to talk about, in chapter 2, the gas laws. So obviously we're going to talk about the gas phase of matter. And we talked a little bit about the different phases of matter, right? What are the three main phases of matter? Solid, liquid, and gas. Okay, in this chapter, we're going to focus with the gas phase. So what are some things you guys remember about the gas phase? What about the space between the molecules?
It's very fast.
They're very far apart. The atoms are very far apart in the gas. And how fast are they moving?
Very fast.
Very fast, very quickly. Okay. So we're going to dedicate a whole chapter to learning a little bit more about gases. Why? Why is that so important in chemistry? Why do you think it would be so important in chemistry?
Because it is everywhere.
Because it's everywhere, right? Our atmosphere, all gases. Do you think it's an important part for chemists to learn about? Absolutely. And so I put some different pictures on this slide. So this equation right here, one of the most famous and well-known equations in chemistry. PV equals nRT. That's called the gas law equation. We're going to use it a lot in this chapter. Okay, what is this right here, guys? What's that?
It's one of those smelly things.
What is it?
Hydraulic
Coal?
stuff. That?
Yeah.
It's like something to make a lot of pressure. Hydraulic stuff.
Okay. Is it a cylinder, a piston, right? Piston and cylinder, like in an engine?
That's not right though.
Oh
Yeah.
Oh yeah.
And so we'll talk about what's going on there, but in your car engine, you're putting in gasoline, gets injected in, it gets spark plug, lights it on fire. And what happens when it gets lit on fire? It burns, and what happens to the space between the molecules?
Shoots up.
It expands, and it pushes up the piston, right?
Star fluid and it kicks back.
Good. So it drives up this piston. Well, the piston's connected to the main drive shaft of the car, which turns the wheels, right? So that's how you drive. That's how you power your car. Anyway, we'll talk a lot about that. Last year we made this year we made a hydrogen balloon. A lot of gases are lighter than air, so they can float. What's happening here?
Hot air.
Hot air balloon. Who's been in a hot air balloon?
I haven't.
Has anyone? A couple of you? I've always wanted to. I never have, but
It's not that fun.
it's not.
Really boring, you know?
The views are great, aren't they?
You can see that in an airplane.
Yeah, but it's not so peaceful and like just floating like that.
Parasailing's like that.
Parasailing,
Not
yeah.
even loud. You
Yeah.
almost want to sleep.
Hey, so tell me how does this work? How does a hot air balloon work? Well, it's hot air, obviously, but how does it work?
Hot air is pushed up into the balloon. Makes it rise.
How? That's what I'm asking. How?
With heat.
Hot air rises. So he's got this torch down here that's heating up the air inside that balloon. But why does it rise? Why does hot air rise? We know it does. Why?
Because it's lighter than cold air.
Why is it lighter than cold air? What happens to the space between the molecules? Expand. So does it become less dense as they expand?
Yes.
Yeah. And something that is less dense will,
Rise.
will rise or float, right?
That's
Yeah. Okay. So just some things that reminded me of this chapter. I threw up a few pictures there. Anyway. Okay, let's get started. Hopefully if you're watching this video, you've got your guided notes out. You're filling them out as we go through these slides. Okay, so what is a gas? Matter exists in three distinct phases: solid, liquid, and gas. So it's one of the main phases of matter. Here's the definition for gas I'd like you to write down in your books. A gas is a phase of matter where the atoms are spread apart and move very quickly. So gas is a phase of matter where the atoms are very spread apart and move very quickly. I don't know if you remember from first year chemistry, we talked about intermolecular forces, these forces that hold molecules together. Well, in the gas phase, these intermolecular forces are very weak, dispersion forces, the weakest ones. And so there's not very much force between these molecules here in the gas phase. So they're free to kind of just move around. They move very quickly. They're spread apart. In a solid, let's just go through it. What are they doing in a solid, guys? What are these atoms doing? Vibrating in place, and they are very close together. The intermolecular forces here are very strong, so they're very close together. What about in the liquid? What are they doing? Good, they're sliding past each other. They're moving faster than a solid, and they're able to slide past each other. Spaced a little bit farther apart, too, with the liquid. That's why it kind of can fill in the shape of the container that it's in. And then what's happening in a gas? Well, they're very far apart, and they're moving very quickly. Okay. We're going to focus the first part of this chapter on pressure. Okay. One of the most obvious properties of a gas is that it exerts pressure on its surrounding. It exerts pressure on the surroundings. An example, a balloon. Is there pressure inside a balloon? Yeah. So if you have a balloon, let me see if I can draw kind of a simple balloon here. You fill it up with air. All the air is pushing on the walls of the balloon and making it expand, right? You blow up the balloon, you put more air in it, it's got more pressure. And that's what's happening. These gas molecules, the air molecules in here, are just pushing against the wall. Same thing in your car tire. You put more air in it, it's got more pressure because those molecules are pushing against the inside of the tire, causing it to have more pressure. But one that's a little bit less obvious, but maybe more important, is that the atmosphere has pressure, doesn't it? Air can exert a pressure, so all the air above us is pushing down and can exert a pressure on us. Can atmospheric pressure change from day to day? Yeah. So on a day like today where it's kind of rainy and cloudy, is it lower pressure or higher pressure, guys? You guys watch the weather?
High.
Yeah, this is a low pressure system. When it's nice and sunny, you see if you watch the weather, you see a big H right over where we live. Nice sunny days. What does that H mean? It's a high pressure. So, yeah, it does change from day to day. Okay, soda can demonstration of pressure. This is what we were going to do today, but you forgot your can, so we're going to do it next time.
Can I go grab one?
So I would like you to bring 2 or 3 just regular sized soda cans. Don't bring any of these huge, whatever you call them. Okay, just a regular 12 fluid ounce.
Do you think it'd work better or be different?
No, we've tried. Actually, it's a little bit harder for it to work as well. It's just too long. So, yeah, just bring a regular sized one. Okay, practice problem number 1. Explain why the soda can collapses. So in order to answer this question, what we're going to do is put it on a hot plate, the soda can. So here's your soda can. We're going to put it on the hot plate. It's going to, well, first of all, we're going to empty everything out. So if you want to bring a full soda can and drink it, that's fine. We're going to empty it all the way out, and then we're going to put a little bit of water, just a little bit of water in the bottom. We're going to put it on the hot plate, and what's going to happen to the water? It's going to start to boil, and it goes from the liquid phase to the gas phase. And so all of these atoms in here are the water is going to become water vapor or steam, right? And so they're spaced pretty far apart. Well, then what we're going to do is set up a beaker of ice water right next to it, and you're going to grab your beaker tongs and quickly grab this can right here and invert it so the can has a little opening at the top, right? So you're going to invert it with your beaker tongs and quickly dunk it in the water. So see how this one's upside down? Yeah. And then you're gonna collapse the can. It's just gonna immediately just collapse all of it. It's pretty cool to watch it. And so that's what you're gonna do next time. Remember to bring your cans. Okay, so this question, explain why. Why does the can collapse like that? Good, Nick. these molecules these water molecules right here are in the gas phase. What's going to happen when you put them in cold ice water or next to it? The space between these molecules is going to do what? Shrink. It's going to get smaller, right? And so all that space right there between them, well, they're going to come together. But when you have it inverted in water, what's going to happen with the pressure inside? Is it going to allow it to equalize with the atmospheric pressure anymore? Nope. And so when you dunk it under and you have it inverted in the water, since those molecules contract, it's going to cause the can to collapse because now the atmospheric pressure is greater than the pressure inside the can. So that's what I would say. The atmospheric pressure becomes greater than the pressure inside the can. So actually what's happening is that the atmospheric pressure is crushing the can. Yep. So that's what I would put for number 1. The space between the water vapor molecules gets smaller, takes up less space, but when it's inverted in the water, the atmospheric pressure crushes the can because it's greater. All right, let's move on. Practice problem number 2. If you got a bag of chips, and you guys might have tried this or seen this if you've traveled in your car, if you have a bag of chips. So let's say you got a bag of chips in Los Angeles, which is at sea level. Obviously, it's right by the ocean. Okay, so you're starting your trip in Los Angeles. And you took this bag of chips with you as you traveled home to Delta, which is around 5,200 feet. What would the bag of chips look like when you got home? Now note, you didn't open the bag. Okay, so it's sealed. So you started at sea level, you came up all the way to Utah. What's the bag of chips going to look like? Like a bubble. Why is it going to look like a bubble? So let me see if I can draw a bag of chips. Probably can't, but maybe I shouldn't have tried. Okay, so you get this bag of chips. Okay, this is in LA. Okay, you travel all the way up to Delta, and what's it going to look like?
Pillow.
Okay, now it looks like a bubble.
Pillow.
Pillow. It's a nice little air pillow. How come?
Because there's more air in Los Angeles than
Okay, kind of. You're on the right track. Why does it look bigger in Delta, guys?
Because the air's different, air pressure.
The air pressure is different here than it is in LA, right? How come?
Lower sea level.
Yeah, they're at sea level. Do they have more air pushing down on them?
Yes.
Yeah. When you come up in elevation, there's less air pressure, right? And so if there's less air pressure, now there's not as much air pressing on the bag, so it can kind of bow out on the sides like this, and it looks like it's a big air pillow. So, differences in pressure, yeah. All right, so you're supposed to draw something or explain it on practice problem number 2. Anyway, I just wanted to put a couple of problems in there to get you thinking about pressure and what happens. Have any of you guys ever gone scuba diving?
Yeah, I've been.
Or snorkeled and you dive down really deep? Or even at the swimming pool? If you dive down, what happens?
Your ears pop and they hurt.
Yeah, why is that? Why is there so much pressure on your ears?
Because you got so much water on you.
Because the water on top of you is pressing down on you, right?
Yes.
Well, the air can be thought of as the same thing. If there's a lot of air pressing down, then it's a lot of pressure. Now it's not as much as water because it's not as dense. But still the same principles apply.
How about when your ears start bleeding? Is that bad?
When your ears start bleeding, is that bad? Probably. I wouldn't think that would be a good thing, yeah. So, okay, measuring pressure. So if there's atmospheric pressure, we've got to find a way to measure it, right? So this is what we use. It's called a barometer. A barometer is a device used to measure atmospheric pressure. So a barometer is a device used to measure atmospheric pressure. Here's a barometer right here. It's got a little dish at the bottom, And it's filled with mercury. Hg is mercury. Mercury is really cool. Why is mercury blue on this periodic table?
It's liquid.
It's a liquid at room temperature, but it's a transition metal. But it's liquid. That's what makes it cool. And so it sits in here in this little dish, and based on the air pressure pushing down on it, so air pressure is pushing down on it, it can cause the mercury to either go up in this column or fall in this column. And they measure it. How do they measure it, guys? In millimeters. So they measure the height of the mercury in this column in millimeters. And 760 millimeters is a pretty common pressure. And so we'll talk about that in a second. So the barometer was invented by an Italian scientist named Evangelista Torricelli. Is that how you say that, guys? Is that how you would pronounce it? Torricelli? Okay, so an Italian scientist, Torricelli. Remember this last name, okay? You're going to see it a little bit in this chapter. So he's the one that invented the barometer, how to measure pressure. Okay, we got mercury in that dish. Pressure makes it rise and fall. Okay, units of pressure. This is where it gets a little complicated because there's a lot of different units for pressure, isn't there? So the most commonly used units for pressure are based on the height of the mercury column in millimeters, like we just showed you, that gas pressure can support. Okay, millimeters of mercury is 1 unit of pressure. mmHg. You'll see that a lot. It stands for millimeters of mercury, and it is a unit of pressure and is often called a torr in honor of Torricelli. So in honor of him, they've given that a unit of pressure. What did Torricelli invent, guys? The barometer. So to kind of honor him, they also call it a torr. So millimeters of mercury and torr are different units of measurements for pressure. Okay, millimeters of mercury and torr are used interchangeably by chemists. They mean the same thing, exactly the same thing. So if you have 100 millimeters of mercury, how many torr do I have? 100. Okay, these units are the same. And that's something we're going to have to remember. Okay, standard atmosphere. This is another unit of pressure. A standard atmosphere, abbreviated, is ATM. It's not an ATM where you get your money out. It's not an automatic teller machine. ATM is how they abbreviate atmosphere. It is a unit of measurement that is equal to 760 millimeters of mercury and 760 torr. Okay, so we'll write this out in your margins. 1 atmosphere is equal to 760 millimeters of Hg and 760 torr. Oh, there it is. Okay, 1 atmosphere is equal to 760 millimeters of mercury and 760 torr. You're supposed to write that in your book. Okay. Units of pressure. So, actually, we should have maybe started with this. What is pressure? How do you measure pressure? Well, it's a force divided by the area that force is applied. It's force divided by the area that force is applied. So I always like to think of like a nail. Okay, so you have this nail right here. Okay, maybe that's a bad picture, but if you step on a nail, Why is that so dangerous?
Goes in your foot.
Because you're putting a lot of pressure, and then, so you've got a lot of force coming down on it, but what's the area right here? Very small. If we divide by a small number, pressure is going to be higher. Okay? So you can put a lot of pressure by stepping on a nail. That's why it's very dangerous. But then you see those nail beds,
Because there's so many of them.
and you can actually lay down. You guys have seen this on like magic shows and stuff. And you can have somebody lay down here. That's a good picture, right?
It's beautiful.
Somebody can actually lay down, and then they put another one on top of them. How come that doesn't hurt them?
There's so many points.
Yeah, there's so many points. So what are you doing with the area here?
It's pretty good.
You're increasing the area. And what happens if you divide by a larger number? Pressure goes down. And so there's not as much pressure on this, so it's not able to actually go into the skin if you use enough of them. So I always like to think about that when you're thinking about pressure. So it's a force divided by area. In the SI system, the units of force is a Newton, which is abbreviated capital N. You guys taking physics?
Nope.
Anyone in here?
Not next year.
In physics, you're going to learn about this a lot. A unit of force is called the Newton, in honor of Isaac Newton. And the unit for area is a square meter. And we know how to find the area of something. Square meter. Length times width, right? So it's meters squared. Thus, the unit for pressure, if we're going to do the units for pressure in the SI system, is the Newton meter squared. Newton divided by meter squared. And this is also called a Pascal. And a Pascal is abbreviated capital P, lowercase a, PA. So Pascal is another unit of pressure that you will see in this chapter. So let's review. Which ones have we talked about so far? Pascal, ATM, which is this atmosphere, standard atmosphere, millimeters of mercury, and torr. Okay, so there's 4 of them, but are there more? Yeah. Let's go through some more. Okay, so here's the conversion factors. Okay? You have to write these in your books. 1 atmosphere is equal to 101,325 pascals. So is a pascal a very large or small unit of pressure? Very small. A pascal is very small unit of pressure. So conversion factors for pressure. 1 atmosphere is equal to 760 millimeters of mercury. It's also equal to 760 torr. Remember, those millimeters of mercury and torr equal the same thing, so that makes sense. 1 atmosphere is also equal to 29.92 inches of mercury. In the United States, sometimes we'll see inches of mercury. Where they measure that column of mercury not in millimeters but in inches. So if it's in inches, that's what you use. There's also, what is this unit of pressure? What is LB, guys? Pounds per square inch. How do you abbreviate this one? Pounds per inches squared. You guys have heard it. How do you abbreviate it? PSI, you've heard of it, right? No. What does PSI stand for? Pound per square inch. Pound per square inch. Okay, when you fill up your basketball or your car tire, what are they measuring it in? PSI. So we see that a lot in America, in the United States. Would you see that in other countries?
No.
No. Because they don't use pounds or inches.
What would they use?
They would use, I don't know, actually. That's a good question. Whether they use atmospheres or millimeters of mercury or torrs, I don't know. That's a good question.
Maybe Google it.
We'll Google it. We'll ask Siri. Okay. So this is the last slide on this video in this section of the notes. So practice problem number 3. Let's go through it. It says your car tire pressure measures 35 psi. Use the conversion factors for pressure to find the pressure in millimeters of mercury and in torr, pascals, and in atmospheres.
Let's go.
So we've got to be able to convert from one unit of pressure to another. So we're going to use those conversion factors.
Why would you have to convert it like that?
Because sometimes you don't want it in psi. What if I ask you how many atmospheres that is?
How often are you going to do that though?
Yeah, how often would you change it like that?
A lot in this
In
chapter.
chemistry, no, like in chemistry.
Yeah, in
actual
chemistry.
experiments.
Yeah, in chemistry. So you have an American chemist who's doing all these pressure measurements. Would it be useful to know how to convert it to the SI units?
Yeah, but would you have to convert it to all of them or just one of them?
Well, just one of them, but in this example problem, I wanted to go to all of them.
Okay.
Just so you got some exposure to doing it to all of them. Okay, here we go. What are we going to start with, guys? We're going to start with 35 psi. That's what it gave us. So put 35 psi, put it over 1. We're just going to use conversion factors, just like stoichiometry. Okay, let's just do it in order. Millimeters of mercury first. Okay. If psi is on top, what's got to go on bottom? psi. Is there a conversion factor that takes psi to millimeters of mercury? Not straight there. Let's write those conversion factors. What was it, guys? 1 atm is equal to what? Okay. 760 millimeters of, you're right, but I'm just going to go with this one first. And 760 torr. And what? How many pascals? 325. How do you abbreviate pascals, guys? PA. What else is there?
29.92 Hg.
Inches of mercury. And what was PSI?
14.7 psi.
How much?
14.7
14.7
psi.
PSI? Okay. Okay, so if we wanted to go to millimeters of mercury.
You put 14.7 on the bottom.
Okay, we got 14.7 psi is equal to how many millimeters of mercury?
So 1. 760.
Well, it's really equal to 1 atmosphere, right?
Yeah. Put 1 on top and
1 atmosphere on top. Now, if we wanted to go to millimeters of mercury, could we keep going?
yeah. So you put the
What needs to be on bottom here?
1.
Atmosphere. In 1 atmosphere, how many millimeters of mercury is there?
760.
760.
Yeah.
Okay. So now all my units will cancel out except for millimeters of Hg. Let's figure out what that is. Good. Perfect. Is that what you guys got?
Yeah.
Okay. So, guys, that's how you convert to millimeters of mercury. What would it be for torr?
Same thing.
Yeah, you could go through all these conversion factors again, but if 760 millimeters of mercury, it's also the same thing as torr. So isn't it going to be 1,809.5 torr? Okay, just to save some time. Now let's go to pascals. Okay, again, we're going to start with 35 psi, put it over 1. Now what would you do, guys? Help me out.
Just get rid of the last conversion and then use the last 2 and get it to atoms, and you can times whatever you want for the.
Okay, so go to atmospheres first then.
Yeah, and you can times whatever you want for the last couple ones.
So PSI's got to go on bottom. We know that there's 14.7 PSI for 1 atmosphere. Okay. And we also know that 1 atmosphere is equal to 101,325 pascals. Atmosphere is on top, it's got to come on bottom. Okay. So 35 times 101,325. Are you guys getting 241,000?
Yep.
250? What's my units again? Pascals. So yeah, Pascal is very small, so that kind of makes sense. 241,000 is a large number. Okay, now we just got one left. Atmospheres. Well, couldn't we just stopped after the second one? So 35 psi, put it over 1. Let's go. We know that psi's got to go on the bottom. There's 14.7 psi in 1 atmosphere. So 35 divided by 14.7, 2.8 or 2.38. Okay, thank you. 2.38 what? ATM. Yeah. Yep, good point. Yep, yeah. But I always like to write it out. I would like to see you guys do this. Okay? Write it out. I want the value and the units. Okay? I think you'll make a lot less errors that way. Okay, so that's pressure conversions. We're going to do a worksheet now in your student workbook. If you'll turn to your student workbook, the worksheet is called Pressure Conversion Worksheet.
What page?
Pressure Conversion Worksheet. And so you've had enough information, you should be able to do that. So hopefully this helps.
What page is it?